When p-type and n-type silicon are placed in contact with one another, it forms a p-n junction. At this junction, an interesting phenomenon occurs that is the foundation of solid-state electronics. A basic p-n junction creates a diode that allows electricity to flow in one direction but not the other. We can see in the diode that the n-type material has free electrons and the p-type material has holes. Near the p-n junction, the electrons diffuse into the vacant holes in the p material, causing a depletion zone. This depletion zone acts like an insulator, preventing other free electrons in the n-type silicon from combining with the holes in the p-type silicon. In addition, this leaves a small electrical imbalance inside the diode. Since the N region is missing some electrons, it has obtained a positive charge, and the extra electrons that fill the holes in the P region have given it a negative charge. Unfortunately, one cannot generate power from this electrical imbalance. However, the stage is set to see how the p-n junction functions as a diode. Now let's connect the diode to an external power source, a battery with a light and a current meter that indicate current flow. The negative terminal of the battery is connected to the n-type silicon. We know that like charges repel, so the free electrons are pushed toward the p-n junction. Similarly, the holes are repelled by the positive terminal of the battery toward the p-n junction. If the voltage pushing the electrons in holes has sufficient strength to overcome the depletion zone, approximately 0.7 volts for a typical silicon diode, the electrons in holes combine at the junction and current passes through the diode. When a diode is arranged this way with a power supply, it is said to be forward biased. In this example, the battery is connected so the negative terminal of the battery connects to the p-type silicon and the positive terminal of the battery connects to the n-type silicon. The negative terminal attracts the positive holes in the p-type silicon, and the positive terminal of the battery attracts the free electrons in the n-type silicon. All the charge carriers are pulled away from the p-n junction, which essentially creates a larger depletion zone and no current flows. When a diode is arranged this way with a power supply, it is said to be reverse biased. A solar cell is essentially a p-n junction with a large surface area. The n-type material is thin to allow light to pass through to the p-n junction. Light travels in packets of energy called photons. The generation of electric current happens inside the depletion zone of the p-n junction. The depletion zone, as explained previously with the diode, is the area around the p-n junction where the electrons from the n-type silicon have diffused into the holes of the p-type material. When a photon of light is absorbed by one of these atoms in the n-type silicon, it will dislodge an electron, creating a free electron and a hole. The free electron and hole have sufficient energy to jump out of the depletion zone. If a wire is connected from the cathode n-type silicon to the anode p-type silicon, electrons will flow through the wire. The electron is attracted to the positive charge of the p-type material and travels through the external load, creating a flow of electric current. The hole created by the dislodged electron is attracted to the negative charge of n-type material and migrates to the back electrical contact. As the electron enters the p-type silicon from the back electrical contact, it combines with the hole, restoring the electrical neutrality. A light-emitting diode, or LED, is very similar to the standard diode we already looked at. LEDs are made to emit light at the p-n junction. When forward biased, the excited electrons from the n-type silicon combine with the holes in the p-type silicon and emit photons of light. Typically, LEDs only emit one color of light. The manufacturer can adjust the frequency of the emitted light from an LED from infrared to ultraviolet.